Now we want to look at the runtime of the binary search algorithm. So I'm going to go ahead and write it up over here. It's going to be T of n is equal to T of n over 2 plus some constant time C. Now, how do we go ahead and solve something like this? So we saw it with the merge sort algorithm that we're going to have to go through a few instances to test out exactly what this is going to be. This one's going to be easier because there's not many things that are going to be changing. I want to go through a few loops to see what the pattern is, and then we're going to go and try to find the big O or the theta, however you want to call it, for the binary search algorithm to see how fast it runs. And it runs pretty quickly, so it's awesome. So we're going to go ahead, and we know that we will need to figure out what T of n over 2 is going to be. So what exactly is going to be T of n over 2 so we can plug it into this equation? Well, pretty much, we're just going to go ahead and use the T of n algorithm, and we're going to divide everything that has an n by 2, right? So anytime you see an n, put a 2 under it. So in this case, T of n over 2 is going to be T of n over 4 plus C. The C is not going to change, right? The C doesn't have an n attached to it, so you will not need to, affect that at all. And now we want to plug this into the original equation. So we are going to plug this. You're going to plug this in to over here, right? So we're going to write it out and then plug it in, write it out and plug it in. So we can start to see a pattern form. And then as soon as we spot that pattern, we can stop doing this and we can move on to trying to write it out a bit more, in the big O notation or with theta. So right now we plug this in. We have n over 2, so we can go ahead and say that T of n is going to be equal to, I guess I put big brackets over here, T n over 2 plus C, just put in the brackets so it's a bit easier to visualize, plus C, and this obviously will be T of n over 4 plus 2C. Well, let's go ahead and do one more run through. We'll need to figure out what T of n over 4 is going to be. We can go ahead and take our T of n over 2 and then divide where we see our n's by 2, which is simply just going to be T of n over 8 plus C. We can see how this is just going to be an easy pattern. So let's go ahead and plug this back into T of n over here. We'll plug this into where we see that. And we're going to have T of n over 8. I'll write it quickly this time, is going to be equal to plus 3C. So we can see exactly what the pattern is going to be. This one really isn't very difficult, right? It's just simple. So now we are going to go ahead and write out the general equation. So that will be T of n is equal to T of n over, we can see that this here went from 2 to 4 to 8. That will be that'll be 2 to the power of k. This one over here is just increasing by 1. So as this one, this one starts off with a coefficient of 1 when we saw that this was 2. It had a coefficient of 2 when we saw that the n was over 4. And has a coefficient of 3 when we saw that the n is over 8. You can see how the pattern is increasing. This will just be k. And then we have our constant C. So that's our general equation right over there. And now we want to figure out what this runs in big O time. So this will be, we know that we're going to want to put that n is equal to 2k, right? When we say n is equal to 2k, that would mean that T n over 2k would be T 2k over 2k, which is T to the 1, which is just going to be a constant that is not going to get in our way. It's just going to do its own thing. So we can go down over here, but now we want to replace this k that we have over here, right? We need to do something with this. And unfortunately, when we have this piece of information, how do we isolate that k, right? Well, we're going to use logs for this. I make sure that whenever I try to talk about logs, I really keep it basic because logs confuse a lot of people. That's natural. Nobody really likes logs. They can go fuck themselves. Everybody hates logs. Logs are those things in math class that you try to understand, and if you don't, actually commit time to understanding what they are, then they're going to haunt you for the rest of your life. So let's go ahead, and we know that the log form is going to be log base, and the base is going to be the thing that's affected by the exponent. We have the result. The result is going to be the thing on the other side of the equation, and then that is all equal to exponent, which is going to be the exponent. Simple enough. So we have the result, we have the base, and then we have the exponent. So we can rearrange this as log of n base 2 is equal to k, and then we have the k isolated. So now we can go back to our equation and we could replace this k over here with what we just have, log 2 to the n. So we can go ahead and write this again. So now we have t to the n, or t of n, sorry, is equal to t of 1 plus kc, which is going to be log 2n. And we have the c. So we have all this written over here, and we know that this here is going to be a constant, right? So this here, this t1 is going to be a constant. So this will be c plus log 2n c. We can take that constant out. That constant is not going to have any effect on us. So we can go ahead and essentially do something like this. C is 1 plus log n. This log n over here, obviously this could be k. You can write it as k if you want, but we know that we're going to have it log. So when we have something like this, we are going to have O of 1 plus log n. Does this one have any effect on us right now? Nope. The thing that's going to be controlling the rate of change is going to be the log n. So in the end, this is going to be O log n. And that's very quick. That is very, very quick. It's better than on, right? So a big O of n, a big O of log n is a lot quicker. We always think of log of n as a smaller n. It's an easy way to visualize it. Say you want to compare if n multiplied by n, n multiplied by log n compared to n squared. We know that the first one there would be smaller because log n is a smaller value. So that's a brief breakdown of the runtime of your binary search algorithm, right? The number of steps will be logarithmic to the size of the database. Let's go ahead and write that out, right? Number of steps will be logarithmic to the size of the input. The inputted sorted array to the binary search algorithm. Boom, there we go. So that is the runtime for binary search. That's why it is O log n. If you have any questions, leave them below, and I'll see you in the next video.